This is Olenjolai Moko. I would like to welcome you into fantastic YouTube channel called Tanzania Online A-Level Secondary Schools, in square bracket OLENJOLAIM. This is my official YouTube channel to teach students all about advanced physics, advanced chemistry, advanced mathematics, and basically applied mathematics. So I have been teaching 10 lectures of gravitations, and this now, after I told you the 9 lectures, so in case that you didn't watch that this is your first video, please make sure that you watch some other previous video before you come to the lecture 10 or session 10, because in this lecture mainly I'll be doing the problem solving on gravitational mechanics. Okay, so I'll be combining questions from the different textbooks and also questions from the advanced certificate secondary examination past papers for paper 1 and paper 2. So that the promise that I give you. My intentions, I will solve 5 questions until be the end of this topic according to the syllabus. However, that if you review different past papers, you find also that the concepts of variations of acceleration gravity above the Earth's surface, on the Earth's surface, inside the Earth's surface. So there's a variations of that acceleration gravity. We who used the previous syllabus for advanced secondary schools in the United Republic of Tanzania, we learned that concept. But the current syllabus, even I have gone beyond of what it is demanding me to teach you. But in some of the past papers, even current past papers, for example, 2016 as 2017, you find also some questions test you about the variations of acceleration with gravity. So possibly I might do another lecture, but according to the syllabus, if just we follow the syllabus, what I told you, it's more than what required in the syllabus, including this lecture, right? So that's the point that I wanted to make. So I'm from beautiful, fantastic country, United Republic of Tanzania, and we have problem solving. So as I said that we have solved the 13 examples, if I'm not mistaken, 13, but I gave you another example, 13, yes, 13, 14. The homework is 14. So if you don't write it, the homework was 14. And the homework was very simple, so there's no need for me to waste my time to answer it, because the answer is known. You have to compare with the first year with the escape velocity that determines by another formula. So this is example. This is example 15, right? So example 15, simplest asks you to calculate gravitational potential. Gravitational potential and potential energy, and the potential energy of mass 0.1 kilogram. Roman R at the Earth's surface. At the Earth's surface. So calculate gravitational potential energy at the Earth's surface. And then Roman 2, calculate gravitational potential, that is B, at a height above the Earth's surface. Height above the Earth's surface, equal to its mean radius. Equal to its mean radius. Equal to its mean radius 2r. So the mass of the S is given as 5. So given the mass of the S is equal to 5.98 exponent 24. kilogram. Also, the big given radius of the S, which is represented as R, is 6.37 exponent 6 meter. Also, the value of universal gravitational constant, it is 6.67 exponent negative 11 Newton meter square per kilogram square. Assume the S to be a perfect sphere. Assume the S to be a perfect sphere. So this is among of the longest questions. To be a perfect sphere. Okay? Of uniform mass density. Uniform mass density. Uniform mass density. So that's the question we have to answer as physics students. Solution. Before we solve the problems, let us read it quickly. It's not a difficult question. I've told you this, all the concepts that are required to solve this problem. So you might even solve yourself within 3 minutes. The question says that calculate gravitational potential and potential energy of mass 0.1 kilograms. Roman A at the S's surface and Roman B at the height above the S's surface equal to its mean radius 2r. So that's the height. So at the height above the S's surface equal to its mean radius, which is twice radius of 40 of the S. Twice radius of 40 of the S. So remember that, twice radius of the S. So that's the height. So this is the height above the S's surface. Be careful. I think that's better if I warn you, according to the nature of the question, this, write the conceptual question. And why it's conceptual? Because the part A is not simple, but the part B is a little bit conceptual. You have to be careful, otherwise you'll be wrong or you won't solve the problem. So solution. So let us start with the part A on the S's surface. On the S's surface. So the S's surface. What is required? What will be given? So we give all of this constant. Good. So what is required? The questions require gravitational potential. Gravitational potential. Gravitational potential, yes. What is the notations of gravitational potential? It is V. So that's what we require. Good. I taught you gravitational potential. What the form of gravitational potential? Not the potential difference, but we are talking about the gravitational potential. I told you, in case that you forgot this formula, we say that we take the work done of bringing a body from from infinity to the point divided by the mass of the body. And this work done after the derivations, we used to find is negative what mass of the body times mass of the S times gravitational constant of what radius of the S. So then divided by what? By mass of the body. So gravitational potential on the S's surface is equal to negative mass of the S times universal gravitational constant times radius of the S. So here, in this case, we are talking about a body on the S's surface. So mass of the S, and this is R. Right? So we are looking at the gravitational potential at this point B, let's say. So the gravitational potential from this formula now is equal to the mass of the S, which we have been given as 5.98 exponent 24 kilogram. Then we multiply by what? The universal gravitational constant, which is 6.67 exponent negative 11 Newton meter square, and then square of the kilogram. Then divided by what? Divided by radius. So the radius there is 60.37 exponent 30 exponent 6. And then this is what? Meter. So 1 meter cancel. Okay, and then 1 kilograms and 1 kilograms will cancel. So it means it's what? Newton per kilogram. So gravitational potential, you have to use your scientific calculator, do your computations, very simple computations. So you just take the negative 5.98 exponent 24, you multiply with gravitational constant, which is 6.67 exponent negative 11, then divided by 6.37 exponent 6. Answer is negative 6.262 exponent what? Exponent 7 Newton per kilogram. That's the gravitational potential on the Earth's surface. So therefore, for 1A, you say that for 1A, therefore, the gravitational potential of the body on Earth's surface is negative 6.262 exponent 7 Newton per kilogram. Then we go for part A, but now we want to deal with what is gravitational potential energy, because the potential energy of the mass. So we want to deal with the first step. We say that we call, not the first, this will be, because we had the first step here, of recalling and using the formula. Here we have the second step of computation. So this is computation. And the second step, the third step now. The third step, we have to recall the formula of what? The formula of gravitational potential U. So we say that U is equal to what? U is equal to negative what? Mass of the body times mass of the Earth times gravitational constant. I told you how the radius over radius of the Earth. And then we say that gravitational potential energy in terms now of gravitational potential to be negative mass times what? Gravitational potential. Simplest formula. So the first step now, if you have the formula, say that compute gravitational potential energy. So compute U. So to compute U, we have taken the mass of 40 of the body, it is what? Negative 0.1 kilogram times 30 gravitational potential, which is 6.262 exponent 37 kilogram or Newton per kilogram. So kilogram and kilogram cancel. Okay? So this is kilograms of mass times 30 gravitational potential. So the potential energy for this case is equal to what? So if you multiply that expression, you will end on having, so you have the response, you just multiply with 0.1. Response will be 6.266 exponent 6 joules. Of course, of kilograms to kilograms, we say gravitational potential, it is Newton. Yes, at this point you still have Newton meter. Excuse me. So the unit here is Newton meter. Why Newton meter? Because we cancel the 1 meter is 1 meter. Right? And Newton meter, so this is still what? So here the unit is Newton meter. Be careful about the SMG in physics. So the unit is Newton meter per what? Per kilogram. And this is equivalent to joules per kilogram. Because Newton meter is a unit of weight done. Right? So even this one, at this point we say that we have Newton meter. So we have Newton meter times 40 per kilogram. So that's why this kilograms cancel. So the response now is 6.62 exponent 6 Newton meter, which is equivalent to joules. So therefore, gravitational potential on the S surface, right? Gravitational potential energy is negative 6.26 exponent 30 exponent 6 joules. Okay, so that is all about part A. Let us think now about part B. So part B, we say that we have to find gravitational potential and gravitational potential energy at a height above the Earth's surface equal to its main radius or radius 2r. So that's the one of the concepts that you have to remember in your computation. So there we ended with the first step. So you say that the 50th step, now we're going for B. The 50th step, you say that sketch the problem for you to understand. So you have the Earth's surface with mass localized at the center, which is mass of the Earth. And then we say again, we found gravitational potential on the Earth's surface, for example, at this point A. And this is point O. And this is the radius of the Earth R. Right? And then what happens? This body is taken to the certain height above the Earth's surface. And then it has been taken the height of this orbit right now, or the height of the orbit that revolving around this body, is going to change. So we say that this is this. So then the height from the Earth's surface, remember that this one we call it the Earth's surface. So this we call it the Earth's surface. So it's at the Earth's surface, the distance from the Earth's surface to this point T, or another point which is called point B, this distance we call twice R. Be careful. The distance from the center to the Earth's surface is R. So the distance where the body is 2R above the Earth's surface. So this is the Earth's surface, and this is a body's orbit. Right? So that is. So if that's the case now, we have to be careful in the denominator of the formula. So we say we got the 6th step. We say that let us recall what? Let us recall the formula of what? Call the formula of gravitational potential on the Earth's surface, gravitational potential. So V. So So you say that the formula for gravitational potential is equal to negative what? Mass of the S is universal constant over radius r. Add the normal formula because it's a ratio of work done to the mass of the body. So now we say that the gravitational potential in another orbit is equal to what? Is equal to negative mass of the S. There's universal gravitational constant, but the radius now, the radius of the orbit will be the radius of the S plus the height of the orbit, because remember that the height of the orbit is equal to twice r, right? So you say that if you recall, for example, this formula plus h, so this is the formula of gravitational potential in a particular orbit. So remember that, remember this formula, my dear student. So then we say gravitational potential for that case is equal to what? Is equal to negative mass of the S, there is universal gravitational constant, radius of the S plus twice r. So this one is equal to mass of the S, gravitational constant of what? Ray r. So gravitational potential above the S's surface will be mass of the S, which is 5.98 exponent 24. Universal gravitational constant is what? 6.67 exponent negative 11 divided by 3 r. What's the radius? The radius is equal to 6.37 exponent 6. So this is mass, kilogram, this is Newton, meter square, kilogram squared. And this is meter. So 1 meter, 1 meter cancel. 1 kilogram, 1 kilogram cancel. So this should be negative. So by using a scientific calculator, what do you get? So the final response is negative 3.23, negative 5.23 times O exponent 6 joules per kilogram. Joules per kilogram. So that's the gravitational potential. So part B, the gravitational potential above the S's surface we computed is what? It is negative 5.23 exponent 6 joules kilogram. Okay? So that the value. Be careful in the computation, please. Then we need to find also what is the gravitational potential energy. So this one, so that was the 6th step. This is the 7th step of computation. So now we are going to the 8th step. 8th step on this problem, simple. We need to compute gravitational potential energy, which is U. So I told you that this is equal to negative mass times gravitational potential. So this is gravitational potential energy, and this is the way that it relates. So you are looking for gravitational potential And then you have negative what? Mass. So negative mass of the body is 0.1 kilogram times 30, negative 5.3 or 4.23 exponent 6 joules per kilogram. Kilogram cancel. So then we say that gravitational potential now is equal to what? 5.23 exponent 5. Negative 5.23 exponent 5. Negative 5.23 exponent 35 joules. So impartibly, therefore, the gravitational potential energy is negative 5.23 exponent 5 joules per kilogram. Be careful. Be careful in computation. Okay, so let us go now to the question that I took from Roger Mancaster, or from the physics books called Roger Mancaster. It has 3 parts. Let me present that question. In case you have any questions about these problems that I've been solving, please ask in the comment section. Don't hesitate yourself, ask in the comment section. So this is example 16. Because you had the 12, 13, 14, 15. Example 16. And these questions refer to advanced physics, advanced physics by Roger Mancaster. In abbreviations, we just call Roger Mancaster. Page 100. Using the following notations, this one means mass of the S, then RE, radius of the S, RE, lowercase, E is equal to radius of the S, radius of the radius of the S. And then we have again acceleration due to the gravity at the surface of the S. G is equal to acceleration due to gravity excuse me. G is equal to acceleration due to the gravity. G is equal to acceleration due to gravity at the surface of the S. At the surface of the S. And then say again G represent gravitational constant or universal gravitational constant. So this represents universal gravitational constant. Universal gravitational constant. So we have Roman R, and this is write down an expression for the gravitational potential for the gravitational potential at the S's surface. So a little bit long questions, but it's short very short in its responses. So don't be discouraged and increase your love of physics. So potential at OT at the S's surface. At the S's excuse me, at the S's surface. B, section B of this question is by how much? By how much? Ask your neighbor, by how much? By how much would the gravitational potential, potential PE gravitational potential energy, this is short equal to PE, okay, PE of a body of mass M. Body of mass M. Increase, mass M increase if it were moved from the Earth's surface to infinity. So what we have, the question by how much would the gravitational potential, PE of the body of the mass, increase, okay, increase as if the gravitational potential if we are moved from the Earth's surface from the S's surface to infinity. From the S's surface to infinity. That is part B. Part C is this. Hence, find an expression for the minimum. Hence, find, this is Roger Mancaster, reference textbook. Hence, find. So sometimes in exams, they make up the questions like this. And then you can give up and can say, this is a very difficult questions. Let us see if it's difficult. Hence, find an expression for the minimum velocity. The minimum velocity with which a body could be projected from the S's surface. From the S's surface and they never return. From the S's surface and that body never return. Good news. Never return. Good. No. Never return to where? And never return. Never return. So you've been given the category, which involves Roman 1. You have determined which involves what? G as universal gravitational constant, and also Roman 2, which involves what? Acceleration with the gravity. That's the end of the question from the book called The Advanced Physics, and the answer is Roger Mancaster. Very beautiful, little bit expensive book. Cannot get a new Roger Mancaster in the Republic of Tanzania in a cost of less than 100,000. So it's expensive, but it's good. But the challenge, one of the things that you'll discover, it has many questions compared to to the concept. This is due. This is where called it due. So let us read the question again, because you know the questions has been long, such a way that we can get even lost along the way when you have been reading the questions. Don't worry. Long questions, I want to give you a secret. Whether you are solving problems in chemistry or in physics, long questions are always simple more than short questions. And I will prove as long as you get connected with me. So long questions, they test your understanding. See? Because many students, they don't like to read long questions, long-word questions, especially long-word questions, because they get lost along the way. So they are not good in reading, because this is part of testing comprehensions in case of English language, because you have a part of comprehension. You'll be given a big passage, a passage of maybe 1,000 words, then you have to summarize, write it in short by using 200 and explaining the main objective of the passage. Interesting, so similar. That business you are doing also in physics. So we say that, the question said, using the following notation, ME mass of the S, E radius of the S, G is acceleration due to gravity at the surface of the S, and the capital G represents universal gravitational constant. Write down an expression for the gravitational potential at the S's surface. Can you? Did we cover about that? Can you write? You remember it? So in case that you don't remember it, I told you, you don't need to claim all of the physics formulas. You just know where to start. Okay? That's Roman A. Roman B, by how much will the gravitational potential energy PE of a body of mass m increase as if we are moved from the S's surface to the infinity? Question. And then C, hence find an expression for the minimum velocity. He didn't say that which minimum velocity. The minimum velocity with which a body could be projected from the S's surface and never return, which involves G, which involves what? G as gravitational constant and G as what the acceleration due to the gravity. Okay, so let us answer. It's not a difficult question. We covered everything. Part A, we covered it in lecture 8. Part B, we covered it in lecture 8. Part C, we covered it in lecture 9. So everything is clear. But because of the name of the book, that Advanced Physics by Roger Lancaster, so you get afraid to try questions. All the questions there, they're still testing. However, that they are not daily questions because they test your understanding. So let me help you. Okay? According to the way, the style that I used to teach you, because I don't want you to claim physics or claim chemistry or claim mathematics, you have to derive these expressions, because at the times when we ask if it is final exams or mock exams, you have a lot of things, so you cannot remember like at this moment. So to write down an expression for the gravitational potential, remember the notation for gravitational potential is capital V, right? Okay, is V, the symbol for the gravitational potential, and value is what? Negative mass of the S times universal gravitational constant over radius of the S, which will be givens. Please use the notations has been stated by the question. Be careful about that. Don't use your notations. For instance, here if you use R, the capital R, then you are completely wrong. You didn't answer the question. Here if you use the capital mass, or maybe the capital mass of the S, then you didn't follow the instructions required by the question. So that's the answer for part A. But in case that you don't forget or you don't remember, you may derive it as quickly as possible. So B, we say that we have what B. By how much will the gravitational potential energy of the body of mass M, so this is the mass M, increase as if we are moved from the S's surface to the infinite? What does it mean? In lecture 8, I taught you how to derive the general formula of determining the work done required to take a body from the S's surface, from the infinity to the S's surface. Be careful. So here we have to write gravitational potential when now a body is taken from the S's surface to what? To infinity. From S's surface to what? To infinity. So the gravitational potential for that case, means the potential energy for that case will be what? Is equal to gravitational potential times mass of the body, but positive. Why? Because the body is moving from the S's surface to the infinity. It will be negative if the body is moving from infinity to the S's surface. Be careful. This is physics, my dear student. Physics is beautiful, very beautiful. Beautiful, beautiful subject. Advanced physics, beautiful. So this is the formula for what? For potential energy. So we are done for part B. Part C now, hence find an expression for the minimum velocity. What does it mean? The meanings of minimum velocity is escape velocity. That the means of minimum, we say it is a minimum initial velocity required by the body to be removed completely from the S's gravitational pull or S's gravitational force. And that is called the escape velocity. So which a body could be projected from the S's surface and never return. So when it reaches the infinity, never return. So I taught you how to derive this formula. Sorry, refer lecture 9. Lecture 9, so I taught you how to derive this formula, where we derived it together with my beloved students, my online beloved students, and derived the formula that the velocity, the escape velocity in terms of universal gravitational constant is equal to twice mass of the S times what? Universal gravitational constant G, and then divided by what? radius of the S. That is the answer for Roman C, part 1. Right? Again, the answer for Roman C, part 2 is what? We have the formula for escape velocity in terms of 40, in terms or involves in what? Twice acceleration gravity, and then you have radius of the S. So you are done. But this one asks you, hence find an expression. So you have to derive. Place this one, derive. So this is left for the homework. And also you have to derive. This also is left to the homework to those serious students. Okay, so that's the end of the questions. You see, how do we answer long questions? You might run away if you read a long question and realize that it's long. Okay, so if that's the case now, let us change the beat a little bit, and let us now go to the beauty of physics. So now I'd like to write a conceptual questions. It's not long. This is example 17. Okay, example 17. And write the big word called the concept. The question states like this one. A satellite of mass, satellites of mass 1,000 kilogram, fantastic, 1,000 kilogram, moves, it means 1 ton.